So let's say I apply a force this way. A certain distance we'll call x. What am I doing to the spring if I'm applying a force over a distance? Work. What's the equation for work? For force parallel to distance. Okay? Or in this case, since x is our d, we could write this as F parallel x. Okay? Alright, however, it's not simply, like if I asked you what was the amount of work I did in the last problem, it's not simply 20 times the distance. Why? Because the force is not constant, right? So at the very beginning, I do not have to apply 20 newtons, right? Halfway, how much do I have to apply halfway? 10 newtons. At the end, how much do I have to apply? 20 newtons. What would I have to apply at the very beginning? Nothing. So it's continually changing, right? F equals kx. So as the x increases, the force I have to apply also increases. So I wouldn't be applying 20 newtons the whole time. It would be changing. Yeah?
Wouldn't 20 newtons end up being like the average?
20 wouldn't be the average. So 20 would be, so F equals kx, right? So 20, when I pulled 20 newtons on a 200 newton per meter spring, how far does it go? The 10 centimeters, right? This is the problem we just did. So if I pulled less, how far would it go? If I pulled half, how far would it go? Half, right? So if I pulled with 10, it would only go halfway. So this is the max. So through the whole journey, what would be the average? It would be 10. So 10 would be the average. So when you do this, just remember you have to multiply by the average force. Okay? Well, in this case, let's just do this mathematically. What would be the average force? 10, which is exactly 1/2. Since it's linear, we can simply go 1/2 times the F max times x. Well, what's the equation for F max? Kxx. And what are we left with? 1/2 kx squared.
Just the US.
So if I do a certain amount of work, where does that work now go? Into the spring, potential energy of the spring, which we call US. So that energy would now be stored within the spring, right? Okay. All right, let's do a problem.